In this video, we are to look for the unbiased minimum variance unbiased estimator for the normal distribution using the Cramer-Rao inequality. For more on this topic, you need to subscribe to this channel. Solution. The first thing to do is to recall the Cramer-Rao inequality. The Cramer-Rao inequality states that you get 1 all over n into multiplied by the expectation of into the differential log of our given function f of x theta all over the theta squared. So what it simply means is that this is the PDF given. The next thing to do is to find the log, then differentiate that function with respect to theta. That means this function multiplied by the multiplied by the expectation and multiplied by n. When we do all of this, we now compare it with the Cramer-Rao inequality, which is this, to get our minimum variance unbiased estimator. So if we have our function to be this 1 all over square root of 2 pi exponential negative 1 all over 2 into x minus theta raised to the power of 2. You can still write this as 2 pi exponential 1 all over 2 x minus theta raised to the power of 2. We can still write this function as this. Why we are writing it like this? So that it will be very easy for we to take our log. So now we say take the log. If we take the log, we have ln f of x theta. That means we are taking the log of this function. We'll get negative 1 all over 2 ln 2 pi. If we take the log of an exponential function, we get the same function by removing the exponential sign. So we get that same thing raised to the power of 2. So if we take the log, we'll get something like this. The next thing to do is to take the derivative. That means we differentiate with respect to theta. We are differentiating this function with respect to theta. That means we have covered the whole of this. So differentiating with respect to theta, we say differentiate with respect to theta. If we differentiate with respect to theta, we'll write it this way. Differential log function, the theta will be equal to, if we differentiate this, we get 0 minus, if we differentiate this, we get 1 all over 2 multiplied by, these two will come over here to give us 2 into x minus theta raised to the power of 2 minus 1. So multiplied by, since it's a function of a function, multiplied by minus 1. So we differentiate inside with respect to theta. If we differentiate this, we get 1. That means negative 1, which is this. So we have to rewrite this. This will now be equal to, this will cancel this. Will now be left with negative 1 multiplied by negative sign. We'll have just x minus theta. 2 minus 1 is 1. So we'll have x minus theta. So the next thing to do is to take our square. If we square that function, we'll also take our expectation. So we'll compare it with this. N expectation of our differential ln multiplied by our given function, the theta squared into, now we are putting our square into here. We get as x minus theta squared. We are also putting our expectation. which is expected value of this. So now we know that the expected value of this is also equal to our variance of x. The expected value, the whole of this is equal to the variance of x. Now we've not put our n. We are comparing this now with the Cramér-Rao inequality. So we'll move over to this other side of the board. So we are to compare it with this. If you find this video helpful, you can subscribe to this channel. So comparing it with our Cramér-Rao inequality, we say compare with Cramér-Rao inequality. If we compare it, we have 1 all over n multiplied by our expected value into the mean function of our given PDF all over this squared. Of course, we've taken this, we've done the whole of this, we've done the whole of this. Now, we take the inverse of that function, which is 1 all over the variance of x multiplied by n. So, this gives us finally n into the variance of x. So, this becomes the minimum variance unbiased estimator for the given normal distribution using the Cramér-Rao inequality. Once we follow these procedures, it will be very easy for we to compute the Cramér-Rao inequality or to compute the minimum variance unbiased estimator of any distribution. For more on this topic, you need to subscribe to this channel.